Hello and welcome to lesson 50 of the Additional Maths OCR Freestanding Maths qualification with Mr. Barrow. Today we're going to look at the second part of this paper, the June 2019 paper. So we're going to be looking at questions 11 to 14. In lesson 49, we looked at questions 1 to 10, and now I'm going to go through questions 11 to 14. Please, before you watch this, have a go at those questions yourself. See what you can do. See what information you can gain from those questions. Which are your strengths? Which are your weaknesses? Where do you need more practice? Okay, so don't just watch other people do questions. Do questions yourself. You need to do the practice. You need to do the mathematics. Okay, without further ado, let's have a look at question 11. So, there's a lot of words in this question. John makes wooden toys in his workshop at home. He classifies the toys as small or large. It takes 5 hours to make a small toy and 8 hours to make a large toy. Okay. He works for a maximum of 60 hours each week. Let X be the number of small toys and Y be the number of large toys he makes each week. Write down an inequality giving the time constraint. Okay, so I'm thinking this is probably a linear programming problem. Okay, a linear programming problem is when you have a question with different variables. Here, our variables are numbers of small toys and number of large toys, and we have certain constraints. Okay, so a constraint is something we are constrained by. Here, John is constrained by the amount of time he can spend making toys. So one of his constraints is that he can only work 60 hours at maximum. Okay, he can work less than that, but it says he works for a maximum of 60 hours each week. So that is a constraint for him. Okay, so write down an inequality giving the time constraint. Well, I know that he can work for a maximum of 60 hours. So some people might think, well, just put down work less than or equal to 60. But no, they're talking about an inequality involving the variables that you are given. So involving X and Y. Okay, so let's try and see if we can get a sense of X and Y within the inequality. Okay, X is the number of small toys. Each small toy takes 5 hours to make. So if I made 2 small toys, that would be 10 hours. 3 small toys, that would be 15 hours. 7 small toys, that would be 35 hours. So if I make X small toys, then that will take me a time limit of 5x hours. 5 times the number of small toys, and X is the number of small toys. So 5x there is the time for the number of small toys to be made. Okay, and so accordingly, if 8 hours is the time to make one large toy, and you make Y large toys, 8y will be the time taken for you to create Y large toys. Okay, because 8 hours for each one. So the total time that John will take is 5x plus 8y. So the inequality for the time constraint will be the fact that 5x plus 8y cannot be more than 60 hours. 60 hours is the maximum. So that has to be smaller than or equal to 60. So that there is the inequality for the time constraint. 1 mark. Okay. Next part. John knows from experience that he needs to make at least 3 large toys each week. Okay. He makes X small toys, he makes Y large toys. He needs to make at least 3 large toys. So Y itself has to be more than or equal to 3, because if it's at least 3, it could be 3 or 4 or 5, etc. So Y has to be more than or equal to 3. So in part B, from this information, write down 2 more inequalities. So that sentence there, I have an inequality immediately. I know that Y, the number of large toys, has to be bigger than or equal to 3. Okay, that's going to be one of them. From that sentence, immediately, Y is greater than or equal to 3. The next sentence, the number of large toys, so that's Y, something to do with Y, should be no more than means at most. So no more than, if I say no more than 7, that means it could be anything up to and including 7, but it cannot be 8. It cannot be 7.1. Okay, so no more than 7 would mean less than or equal to 7. So here, y, number of large toys, so y should be no more than, so y is less than or equal to, double the number of small toys, so 2 times the number of small toys, which is x, so 2x. So there's my second one. Okay, so from that second sentence, y is less than or equal to 2x. So my two inequalities that I need to write down for part B are that y is greater than or equal to 3 and that y is smaller than or equal to 2x. Okay. Now, part C. On the grid provided, illustrate these 3 inequalities and then shade the region that is not required. That means what will be left, so the bit that's unshaded will be the required bit. I prefer doing it this way. I prefer shading what's not required. So what you're left with is a nice blank space rather than shading what you do require, because then you might have 3 different parts of shading and then what's required is the bit that's shaded 3 times and then it becomes a mess. So you just shade what's unwanted and what's left is a nice clear blank space. So we need to show these inequalities on this graph. In order to show an inequality on a graph, you draw the line that represents the equality and then you choose one or other side of the line. So for example, for 5x plus 8y is less than or equal to 60, if I wanted to show that on the graph, so I want to show that on this graph here, what I do is firstly I draw the line 5x plus 8y, equals 60. Okay? And I've got to decide, is that going to be a dotted line or a solid line? Because it is a solid line if the line itself is included in the inequality, and it's a dotted line if the line itself is not included. Well, with all 3 of these, the lines will be included because they are less than or equal to or greater than or equal to. So they are all inclusive inequalities, that they include the actual value. Okay, so these will all be solid lines, all 3 of these inequalities. So 5x plus 8y equals 60. How do I draw that? Well, the easiest way to draw an equation of this form, when it's not in the y equals mx plus c form, when it's in this form, ax plus by equals a number, is just simply finding the intercepts, the intercept of the y-axis, the intercept of the x-axis. The intercept of the y-axis, the y will be the y value when x is 0. So when x is 0, 5x will be 0. So then 8y will equal 60. So then all you need to do is 60 divided by 8 to find y, which is 7.5. So I know that 7.5 is the y-intercept. Then I find the x-intercept. The x-intercept is when y is 0. When y is 0, you're on the x-axis. So if y is 0, 8y will be 0, and then 5x will equal 60. So then x will be 60 divided by 5, which is 12. And this is a linear graph. So that there'll be a straight line between those 2 points. And I'll try and draw a straight line. I've just learned how to do that on this. I'm using the shift button, and there we go. There's my straight line, which is relatively good. I could probably make it a little bit better. So undo that. So let's try and do it even better than that, right from there to there. Perfect. Okay. So there's my first line, 5x plus 8y equals 60. Now I want to shade what I do not want. I want the part of this graph, which is the coordinates where 5x plus 8y will be smaller than or equal to 60. One way of doing that is just to choose a coordinate on one side of the line and see if that coordinate works in that inequality. A very easy one is choosing a coordinate on the left side of this line. I'll choose a very, very simple one, 1, 1. So x is 1 and y is 1. If x is 1, 5x's will be 5. If y is 1, 8y's will be 8. Is 5 plus 8 less than or equal to 60? Yes, it is. Okay, so we do want that coordinate 1, 1. So we do want this side of the line. So what we don't want is we don't want everything on the other side of the line. So we don't want that part of the graph. So I'm shading that because I'm shading what I do not require. Okay, next. Y is greater than or equal to 3. So this time I'm going to choose just a different color, and I'm going to do this one in red. If the y coordinate has to be bigger than or equal to 3, I draw y equals 3 as a solid line. Y equals 3 is this horizontal line that goes through, didn't quite work there. Let's try that again. Goes through y equals 3 just there. Okay. And I want y to be greater than or equal to 3, so I want above that line. So I do not want below that line. I don't want y coordinates below 3. I want y coordinates greater than or equal to 3. So I don't want this side. That was the easiest one. And the next one, which I'll do in blue, y is less than or equal to 2x. So I draw y equals 2x, and then I decide which side of the line I want and which side of the line I don't want. Y equals 2x goes through 0, 0, goes through 1, 2, goes through 2, 4, goes through 3, 6, goes through 4, 8, etc. The y coordinate is double the x coordinate. So let's just try and draw that with a straight line. Approximately like that. Okay. So next, I want the side of that line where the y coordinate is smaller than or equal to 2x. So let's just choose a coordinate on one side of the line. So let's choose the coordinate 3, 4. Okay, so that's on this side of the line. Does that work in that inequality? If x is 3, 2x's will be 6. Okay, so that'll be 6 there. And y was 4. Is 4 less than or equal to 6? Yes, it is. So I do want that side of the line, so I don't want the other side. So I don't want all over there. So what I've ended up with is I've ended up with this little triangle here, where anything inside the triangle is allowed. Now we're talking about toys, the number of toys made. We will be making whole numbers of toys, so it's not like anywhere in this region is allowed. I can't have the point, let's try and choose a different, I'll choose green. I can't have the points here where I've made 3.5 small toys and 4.5 large toys. So that coordinate there doesn't work. It's only going to be integer coordinates for this question. So I'm going to put a green dot at every point where there is a possible solution. So here, because I'm allowed to be on the line, so that's allowed. That's allowed. That one. That one. I'm only doing this to help me with later questions. Okay, I've finished with part C of this question, but I'm just putting in with dots the allowable points. I'm just going to check this one, whether it is on the line. 4, 5. If I substitute 4, 5 into this equation here, does it work? So if x is 4, 5 4s are 20. If y is 5, 8 5s are 40. 20 plus 40 is 60. Yes, it's exactly on that line. So that coordinate works. There we go. There we go. There we go. And then also 7 3 is just, I think, it's definitely on or above the red line. Is it in this line? 7 3. So if I plug 7 in for x, I get 5 7s are 35. If I plug 3 in for y, 8 3s are 24. 35 plus 24 is 59, which does work. Okay, that is below the line, so that would be on just under the line. 5x plus 8y equals 60, so it would be within the region 5x plus 8y is less than or equal to 60, so that's fine. Okay, so those are the coordinates which I'm allowed to make. I'm allowed to make those numbers of toys. Okay, or John is allowed to make those number of toys. I'm not the toy maker, John is. So let's see the next part of the question. Part D. Find the maximum number of toys that John can make in a week. Okay, and the number of hours he would take to make them. Now these green dots are now going to help me. So I'm looking at the green dots and I'm thinking, which of those possible solutions gives me the maximum number of toys that John can make? Okay, so I want the maximum number of toys John can make. So John makes X small toys and Y large toys. So the objective function, which is usually used as P, okay, so if it's the maximum number of toys, it's X plus Y, because it's just asking for the total number of toys he makes. So I want to use those coordinates and decide which of those coordinates, and I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 possible solutions, 12 possible coordinates. He can choose to make those number of toys. Which one gives him the greatest for X plus Y? Okay. Usually your solutions are near the vertices. Okay, so near this vertex, you've got sort of these two solutions there. Near this vertex, you've got this solution. And then near this vertex, this solution, or these solutions. Now, we want the greatest number for the x coordinate plus the y coordinate. So we're probably going to be looking at this coordinate there or this coordinate there. Okay. And just looking at them, it's quite clear that 7, 3 is probably going to be better than 4, 5. 7 plus 3 is 10. 4 plus 5 is 9. So 7, 3 will get us, that coordinate there will get us the greatest number of toys made. It'll get us 10 toys made. Okay. So at 7, 3, P equals 7 plus 3, which is 10. So 10 toys made. And we want the number of hours he would take to make them. Now it takes, like we remember, okay, 5 hours for every small toy, 8 hours for every large toy. So it's 5x plus 8y is the number of hours. Okay, so for this, 5x plus 8y would be 5 lots of 7 plus 8 lots of 3, which I've already done to check that that worked, and that was 59. So that takes 59 hours, okay, to make the most number of toys he could make. Okay. Now, the next part, 3 marks for part E. The price for which John sells his wooden toys is such that the profit made, okay, the profit made is £28 for every small toy and £60 for every large toy. So if he sells 2 small toys, that will be 2 28s or £56 profit. And if he sells 7 large toys, then that would be 7 lots of 60, so £420 for that many large toys. So the profit, which is our objective function here, is 28 times every small toy. So there are x small toys, so it's 28x, and 60 times y, so it's plus 60y. That is the profit function. So we want to find out which of these coordinates gives us our greatest profit. So you might think, oh, I'll just plug 7, 3 in. But actually, he gets much more profit for large toys. So you kind of want to maximize the number of large toys. So you're probably going to be choosing between the original one, 7, 3, maybe this one here, but probably this one here. Okay, so I'm just going to check those 3 coordinates. I'm not going to bother with the others because the others have the same amount of one type of toy, but less of another type of toy. So if you make less toys, you're going to have less profit because every toy you make has extra profit. So I'm just going to substitute for each of those 3 coordinates. So we've got 4, 5, we've got 5, 4, and we've got 7, 3. Okay, so at 4, 5, the profit is 28 4s plus 60 5s, which gives me 412. At 5, 4, the profit is 5 lots of 28 plus 4 lots of 60, which is 380, which isn't surprising because if you have here, they've got the same number of toys created, both 9 toys, but in the top one, you have more large toys, and large toys give you more profit. So it should give you the better amount of profit. And the last one, 7, 3, 7 28s and 3 60s is 376. So the best option is 4, 5, and he makes £412 profit. So it says there, assuming at the end of each week he sells all the toys, find the number of each type of toy he should make to maximize his profit and calculate the profit in this case. Okay, so make 4 small and 5 large, and then profit would equal £412. Okay, and that's that question. It's a lovely question. I love linear programming. And let's have a quick look at the mark scheme. Okay, a lot less work on the mark scheme than I seem to do, but same ideas. It doesn't say you have to really show all the different points, but it's a good idea to just show that you've tried different points and not just gone for one answer, because you need to check with yourself which ones are likely to be the correct answer, and just make sure by checking against other points. If you want more practice on this, my lesson on linear programming is lesson 13 in my channel. Okay, right, let's have a look at question 12. So in this question, the curve C1 has an equation y equals 10x minus x squared plus k. So that's a negative quadratic, okay? And that curve passes through the point 510. So a negative quadratic. So we'll look something like this. So that's not this graph here. The graph that's shown below, part C, on the drawing paper is a different graph, okay? The curve C1 has that equation and it passes through the point 510. Show that k is equal to negative 15. Okay, so we need to use the knowledge that we have a coordinate on this graph and we have the equation, which is missing a little bit of information. So we need to use the information from the coordinate to work out the value of k. Okay, so that's a simple substitution question. We know that when x is 5, y is 10. So I can replace y with 10 and x with 5. So 10 is equal to 10 lots of 5 minus 5 squared plus k. So 10 is equal to 50 minus 25 plus k. So 50 take away 25 is 25. 25 plus k is 10, and therefore k is negative 15. Which is what we wanted. Okay, so that part's done. We've shown that k is minus 15. So we now have an equation, y is equal to 10x minus x squared minus 15. That is our equation. Okay. Part B, show that there is a maximum value at the point 510. Okay, we're given the point 510. We now have to show that there's a maximum at that point. There are different ways of finding the maximum. For a quadratic, we could find the maximum point because that's the vertex by completing the square. That's not necessarily that easy for this. I would prefer to maybe, in this case, because this is a negative quadratic, might get some errors with my algebra with negatives. I'll probably use differentiation. To find a maximum point, we know that a maximum point has a gradient of 0. Okay, so at a maximum point, so at this maximum that we drew here, we drew this negative quadratic. At that maximum point, if we drew a tangent to the maximum point, that would have a gradient of 0. So to find the gradient, all we need to do is differentiate. So let's do that. dy by dx is equal to, now when I differentiate, 10x differentiates to 10 because x to the power of 1, the power goes in front, so 1 multiplied by 10, and then the power drops by 1. From x to the power of 1, it becomes x to the power of 0, and x to the power of 0 is just a number of 1. So 10x differentiates to 10. Negative x squared differentiates to minus 2 lots of x to the power of 1, so just minus 2x. And then minus 15 differentiates to 0, because minus 15 is in effect minus 15x to the power of 0. And when that power 0 comes in front, 0 times negative 15 is 0. So any constant will differentiate to 0. So dy by dx is just 10 minus 2x. So we want to find when that is equal to 0. Okay, so at the maximum, 10 minus 2x will equal 0. So add 2x both sides, 10 equals 2x, divide by 2, x is 5. Good, so I found the x coordinate, x is 5. And when x is 5, y is equal to, and I substitute 5 into the equation of the quadratic, not into the equation of the gradient, because that would just give me 0. I plug 5 in, so it becomes 10 lots of 5 minus 5 squared minus 15. And that is equal to 50, take away 25, take away 15, which is 10. So I know that 5, 10 is the maximum point. So that's part B. Okay. Next bit. The curve C2 with equation y equals x minus 3 all squared has been plotted on the grid provided. A classic positive quadratic, which is, it's nicely already in completed square form. And as you can see, this, if you know your transformations of graphs, is just a translation of 3 to the right of the original y equals x squared graph. That's why the vertex is now at 3, 0 rather than at 0, 0. Okay. On the same grid, sketch the curve C1. So we want to sketch this curve on the graph, so we have both curves on that graph. Well, one way is just to plot some points, okay? So if we plug in the values 0, 1, 2, 3, 4, 5, 6, 7, 8, and then plot those points, then we should get a nice smooth curve. We already know that 5, 10 is on the graph. If we plot some other points, 0 would be negative 15, so that's not on the graph. 1 plugged in will give you minus 6. 2 plugged into this function, into this quadratic, would give me 1. So 2, 1 is on the graph. Oh, that looks like it's a point where they both cross. 3 gives me 6. 4 gives me 9. 5 gives me 10. And since that's the maximum point and quadratics are nicely symmetrical, it should be 6 goes back to 9, 7 goes back to 6, and 8 goes back to 1. So it's nicely symmetrical either side of the maximum point. And I will sketch that, hopefully a nice smoothish curve. Apologies for my terrible drawing. And there it is. Okay, I think I would get full marks for that. Find the coordinates of the points of intersection of the curve C1 and C2. Well, by plotting it, I've got the coordinates of the intersection. Okay, that's these green points there and there. That's where they cross. Okay, so part D, all I need to write down is that they cross at 2, 1, and 6, 9. Okay, so those are the two coordinates of the points of intersection of the curves. Part E, find the area between the curves. Now, this is the nice part of this question. This is where it gets fun. Okay, so here we want to find the area between these two curves. If you've done your integration, your calculus, then you know that the area between the x-axis and a curve is given by definite integration. If you want to find the area between two curves, what we want is basically the sum of all of these infinite differences between the curves. Okay, so if we sum up all these infinitely many vertical lines between these two curves, okay, then it'll give us the area between those two curves. Okay, so those vertical lines are the difference between the two curves. They are the purple curve, subtract the black curve will give us those differences. Okay, so the area between two curves is in effect the integral, the sum of the top curve, so that's my 10x minus x squared minus 15, subtract the bottom curve. Okay, so this time, let's just change the color. The other curve was x minus 3 all squared, and I'm just going to expand that to x squared minus 6x plus 9, okay, with respect to x. So if I integrate the difference between those two curves, then that will give me the sum of all those vertical lines, which will then create that space, that area. But I need to do it between two limits. I need to stop at some point. So I need to start when x is 2, and I need to stop when x is 6. So I need to integrate between 2 and 6, because those are my starting points when the start of the area begins and the end of the area. Okay, the two x values for the two x coordinates where the two curves meet. Okay. Before I do my integration, I'm going to subtract and make it a little bit simpler for myself. So what's that equal to? That's equal to 10x minus x squared minus 15. Take away x squared minus 6x plus 9. I'm going to write it in order of the quadratic part, so the x squared part, then the linear part, the x part, and then the constant. So negative x squared, take away another x squared is negative 2x squared. 10x minus 6x, so that's positive 16x. Minus 15 minus positive 9 is minus 24, or negative 24. So now I just have 3 items that I need to integrate. When I integrate, if I'm doing a definite integral, I put my result in these brackets, and then I substitute in the values of the limits. So when I integrate, I raise the power by 1 and I divide by the new power. So minus 2x squared becomes minus 2x to the power of 3 divided by 3, so that's minus 2/3 x to the power of 3. 16x becomes 16x to the power of 2 divided by 2, so that becomes 8x squared. And minus 24 becomes minus 24x to the power of 1 divided by 1, which is just minus 24x. And at this point, I then substitute in 6. And using my calculator, if I substitute 6 into that whole expression instead of x, that gives me 0. And then if I subtract the result when I substitute in 2. And if I substitute 2 into that expression, that gives me negative 64/3. So it's 0, take away negative 64/3, which is positive 64/3. So 64/3 is the area between those two curves, and that is units squared, square units, because that is area. Okay, find the area between curves C1 and C2, and that is it. Okay, the other way could have been, you could have found the area below the purple curve between the x-axis and the purple curve, and then the area between the black curve and the x-axis, and then subtracted the two from each other to get the green area. But it's a longer process. You have to do more integration and more substitution. So I would prefer to subtract the two functions from each other, then integrate. Let's have a look at the mark scheme. As you can see, the mark scheme has this alternative method, which is about doing them separately between 2 and 6 for one, between 2 and 6 and the other. Lots of integration, twice as much integration, twice as much substitution for the same amount of marks. Okay, so if you need to practice this a bit more, so I said that you could complete the square, so that was the alternative method to find the maximum point, but the differentiation was probably quicker. But if you want practice completing the square with more difficult things like that, then see my lesson 5. If you want practice with stationary points, so finding the maximum point, that's my lesson 38. And practice with this last part, area between two curves, that's my lesson 44. Okay, let's move on. Next question. Question 13. Aha, this looks like it might be a 3-dimensional trigonometry question. Lovely. Now, the problem with these is that it's very difficult to show on a diagram a 3-dimensional drawing, okay, because you've got a 2-dimensional piece of paper. Okay, I'm going to try and see if I can draw that so it looks easier for us to notice what's going on. Okay, a straight road runs on a bearing of 60 degrees from a point A to a point B, which is 400 meters away. A vertical mast, C to T, stands at a point C 300 meters due north of A. It's weird because the north is not up the page, it's sort of at an angle, so that A to C, that is north, of the north direction. Okay. From the point A, the angle of elevation of the top of the mast, T, is 7 degrees. Okay. The triangle ABC is on horizontal ground. Okay, so I'm going to try and represent that as best I can up here. So I'm going to draw a sort of part of a plane. A plane is a two-dimensional surface like the top of your table or your exercise book, etc. And this plane, okay, is the horizontal ground. Okay, so ABC is on this plane. So let's say A is here, and let's say that north is this direction. Okay, so north is that direction. So A to C, let's say C is there. So that's A. C is up here somewhere. And that's 300 meters away. And then B is 60 degrees over here, so and 400 meters. That's 60 degrees. And that's B. So A, B, and C are all on horizontal ground. Okay, and then T, I'm going to use a different color for T. Okay, T is up in the sky. It's perpendicular to this plane, so it's coming out of the surface. So T is a mast, okay, up there in the sky, away from the ground, perpendicular to AC and perpendicular, so at right angles to CB. Okay, so it's perpendicular to anything that's on the ground, straight up in the sky. And the angle of elevation of T from A is 7 degrees. So this green line is also going out off the surface. So 7 degrees is there. Okay. I hope that drawing makes it slightly clearer. Okay. Practice doing sort of drawings where you're trying to show perspective and trying to show three-dimensional within a sort of from a two-dimensional drawing. It's difficult, but you can get that sense by sort of drawing a part of the plane like I've done there. Okay. So we want to find the height of the mast. So that's the distance from C to T. Okay, well, I've got a nice right angle triangle. I've got a right angle triangle. I'm going to draw it sort of just basically on. So there's A, there's C, and T is straight up. I know that that's not 400, that's 300 meters. I know that's at right angles, and I know this is 7 degrees. Okay, so that's easy. I can find the height TC because I know my right angle trigonometry. Okay, so I want to find the opposite side. I've got the adjacent side, and I've got the angle 7 degrees. So I know I'm going to be using tan. So tan of the angle 7 degrees, so tan of 7, is equal to the opposite, which is what I want, the length TC, so this height, over 300. So if I do 300 multiplied by tan 7, that would give me H. So H is 300 times tan 7, which is 36.8 degrees to 1 decimal place. Let me just check my workings because I did that earlier. 300 times tan 7. Make sure your calculator's in degrees mode. 36.835. So yes, 36.8 degrees to 1 decimal place. Okay, so that's part A done. Part B. Find the angle of elevation of the top of the mast from point B. Okay. So this is now asking for, if I go from B and I'm looking up at the top of the tower, I want the angle of elevation. So firstly, I'm looking from B to C straight along the ground. And then if I raise my eyes up till I'm looking at the top of the tower, so at the top of T, what angle have I raised my eyes by? Okay, so that's another right angle triangle. However, do I have enough information? I need to find this angle of elevation, so I'm going to call it theta. Okay, this lovely Greek letter we use for unknown angles. And I need, in order to find theta, I need, in that right angle triangle, I need 2 lengths. At the moment, I've got 1 length. Okay, well, for example, apologies, earlier I said the height of the triangle is 36.8 degrees. Clearly it's not in degrees. 36.8 meters. Apologies. Well done if you were shouting that out at me. Okay, 36.8 meters. So I know that distance there, that orange distance, okay, is 36.8 to 1 decimal place. I should use the whole answer from my calculator. So what I need to find is I need to find another length. So it's probably best if I find the length C to B. Okay, so this blue length here, C to B. I have in this triangle ABC, okay, so that triangle ABC, 400, I have 300, and I have 60 degrees, and all I want to find is this length there. I'm going to call that little a, okay, because if I have two other lengths in a non-right angle triangle and in the angle, then I can use the cosine rule. So I know that a squared equals b squared plus c squared minus 2bc cos a. So if I'm calling it a, then this angle 60 is capital A because it's opposite it. So that a squared would equal 300 squared plus 400 squared minus 2 lots of 300 times 400 times cos of 60. And I substitute that in my calculator, and that gives me, for the length A, not a squared, but for the length A, 360.55 dot dot dot. I'm not going to round it because I want to keep the number that's in my calculator, okay? Because you shouldn't round and then use a rounded number in further calculations. You should use the full exact value from your calculator. Okay, so I've done that. So I now have these two lengths. I know that's 360.55 dot dot dot. So I have now two lengths in that right angle triangle. So I'm going to draw that right angle triangle here. I know this is 36.8-ish, 83 dot dot dot. So I need to use the full number. I know this is 360.55 dot dot dot. And I want to find theta. So I know that tan theta is equal to 36.83 dot 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 over 360.55 dot dot dot. And therefore theta is the inverse tan of that fraction. So tan to the minus 1 of the answer that's in my calculator from that fraction. And that gives me, when I've done that, 5.8 degrees. This one is degrees because it is an angle to 1 decimal place. Okay, so the angle of elevation of the top of the mast from point B is 5.8 degrees to 1 decimal place. Right. Part C. Find the bearing of the base of the mast from point B. The bearing of the base of the mast from point B. Okay, so the direction you need to face if you want to look at C from B. Okay, so looking at my diagram, I'm just going to zoom in a little bit. I know north is sort of this direction. I know that if I continued this line from A to B, kept it going, then this angle here would correspond with this angle. So that would be 60. I know that this would be 180. And since the bearing is an angle measured clockwise from north, then the angle I really want is this, let me choose a different color, this sort of orange angle clockwise from north all the way to there. So all I need to find is the final angle at B in this triangle. So this angle here, let's call that alpha. So I want to find alpha, and once I've found alpha, I'm then going to add 60 and 180 to it. I've got my bearing. Okay. Now, if I want to find an unknown angle in a non-right angle triangle, I either need to use the sine rule or the cosine rule. I have all three lengths, so I could use the cosine rule rearranged. I have also got an angle in there and its opposite length, and then the opposite length to alpha is 300 meters, so I could use the sine rule as well. Okay, so either way, I'm going to use the cosine rule just because I like it so much. Okay, so I would rearrange the cosine rule. I know the cosine rule can rearrange to cos of A equals b squared plus c squared minus a squared over 2bc. And where a is opposite the angle that I want to find. Okay, so here actually I'm trying to find angle b, so I'm really looking at this side as being the one opposite it. So the 300 is opposite alpha. Okay, so cos alpha is 400 squared plus 360.55 ... squared minus 300 squared, because the 300 is opposite the alpha, over 2 times 400 times 360.55 ... And once I've found that, I then do the inverse cos of the answer, so cos to minus 1 of the answer, to get my value of alpha. And if I do that correctly, then my value of alpha is 46.1 to 1 decimal place. And then I said that I would just add that to 60 and to 180, and I've got then my bearing. So I will add the bearing is 60 plus 180 plus alpha. So that is 286.1 degrees, but the bearing's usually given three digits rather than with decimal places, so 286 degrees to the nearest whole. Okay. So there's the mark scheme for that question. So feel free to pause and have a look at that yourself. If you want practice on this, 3D trigonometry, lesson 18 is where I go into that. There's also other lessons on the sine rule and the cosine rule and things like that. But 3D trigonometry is what this is. Okay. So let's go on to the last question. Question 14. All right. Speed bumps. Lovely. Speed bumps are designed to encourage drivers to drive slowly. On a particular road, the bumps put onto the road are designed to give minimum discomfort and damage at a speed of 9 meters per second. Okay, so if you're going at 9 meters per second, you should get very little discomfort and damage. Brilliant. Paul is driving along the road at the speed of 14 meters per second. Oh no, he's going to have maximum or more discomfort and damage. So when he sees the warning sign, he is 50 meters before the first bump. And so because he's sensible, he immediately slows down with uniform deceleration, so that when he reaches the first bump, he is traveling at a speed of 9 meters per second, as suggested. So, part A, calculate the uniform deceleration. So it's uniform deceleration. If you have constant, which is what uniform means it doesn't change. If you have constant acceleration, you are able to use SUVAT. Okay, so the SUVAT formulae, the constant acceleration formulae for S, U, V, A, and T, so displacement, initial velocity, final velocity, acceleration, and time, so those different formulae, which hopefully you've memorized, can be used in part A because you've got uniform deceleration. So what do we know? We know at the warning sign, okay, he goes from the warning sign to the bump. So his speed at the warning sign is his initial velocity. So part A, we have an initial velocity u of 14. We have a final velocity because when he reaches the bump, when he hits the bump, he is going at final velocity of 9 meters per second. And we know the distance between those, the displacement he's gone between those is 50. So we have those three values and we want to find the uniform deceleration. So we want to find A. So we need to find the SUVAT equation which links U, V, S, and A. And that is the one which is V squared equals U squared plus 2AS. Okay. And if we substitute all those in, we get V squared is 81 equals U squared, which is 196, plus 2 times A times S, which is plus 2 times A times 50, which is plus 100A. And then if we subtract 196 and then divide by 100, we get negative 1.15 for A. So the value of A is minus 1.15. meters per second per second. Okay, so he is decelerating at a rate of 1.15 meters per second every second. So he's reducing his speed by 1.15 meters per second every second. So calculate the uniform deceleration and the time taken. We need to find the time as well. So let's just use our initial 3 values, and we want to find t. So what Suvat equation links those 4 things? So u, v, s, and t. That would be the one that is displacement is your average velocity, so half of u plus v, multiplied by the time taken. So if we substitute the values in 14, 9, and 50 in there, we should be able to find t. Okay, so I'm just going to rearrange that to make t equals, because I prefer doing that before I substitute things in. So I'll multiply by 2, so 2s equals u plus v lots of t, and then divide by u plus v, so 2s over u plus v. So substituting in 50 for s and 14 and 9 for u and v, we get t equals 50 divided by 23. Okay. When I say 50, I obviously mean 100, because it's 2s, not 1s. Honestly, Mr. Barry. So that's about 4.35 seconds to 2 decimal places, or to 3 significant figures. Okay. So that's the time taken, 4.35 seconds. Right. Immediately after the bump, he accelerates such that at t seconds after leaving the bump, his speed, v, is given by v equals 1/100th of 15t squared minus t cubed plus 9. Okay. So now we have acceleration such that the velocity is given by this formula. Okay. It doesn't say it's a uniform acceleration, it just says acceleration. So we probably can't use Suvat anymore. In fact, if the velocity is a cubic function, then the acceleration itself, because acceleration is your rate of change of your velocity, acceleration will be quadratic, and hence you won't have uniform acceleration. It'll be changing. It'll depend on the value of t. Okay, so we can't use Suvat from now. So part B, show that he reaches his original speed of 14 meters per second in 10 seconds. Well, we've got the formula for his velocity. Okay, so when t is 10, we can just substitute that in, I guess. So when t is 10, the velocity will be 1/100th of 15 lots of 10 squared minus 10 cubed, and then plus 9. And lo and behold, that equals 14. All right, we've done it. There's only 1 mark for that. That was just a substitution. Okay. Find the distance traveled from the speed bump by the time he reaches this speed. Okay. So how far has he traveled, has Paul traveled in those 10 seconds? There are a couple of ways of doing this. Either you use the velocity formula and you've created a formula for the displacement, and you substitute in t is 10 into that, or you use definite integration between 0 and 10, and the displacement will be it's like the area underneath the velocity time graph gives you your distance traveled. And so definite integration between 0 and 10 will find that distance. Okay. I'm going to do the first one, which is integrating to find an expression for the displacement, because if you integrate velocity, you get displacement. Because if you differentiate displacement, you get velocity. The velocity is like the gradient of your displacement time graph. Velocity is the rate at which your displacement is changing over time. How many meters per second? That is the gradient of displacement. Okay, so if velocity is the gradient of displacement, then displacement is the integral of velocity. Okay, so let's find that. So if velocity is 1/100th, I'm going to rewrite that out, but I'm going to write it separately, not in brackets. So I've got 15t squared over 100 minus t cubed over 100, and then plus 9. And what am I doing? Yes, I'm writing it in the space where I should be doing part D. So I'll write it over here. B equals 15t squared over 100 minus t cubed over 100 plus 9. So displacement is the integral of that. So if I integrate 15t squared over 100, I get 15t cubed over 100 divided by 3, okay, which is 5t cubed over 100. So, or 5/100ths of t cubed. Minus, if I integrate t cubed over 100, I get t to the power of 4 over 100 divided by 4, which is t to the power of 4 over 400. And then if I integrate 9, I get 9t. And then I get plus c. Now this constant, since my displacement, my distance traveled is 0 at the start, okay, when I leave that bump, my distance traveled is 0. So when t is 0, my displacement is 0, then c will, if I substitute t is 0 and s is 0, you get the value that c is 0. So I'm just going to erase that, okay? So that's my expression for my displacement. And then when t is 10, my displacement will be 5 times 10 cubed over 100. So 5 times 10 cubed is 5,000, divided by 100 is 50, minus 10 to the power of 4, okay? So 10,000 divided by 400, which is 25, and then plus 9 times 10, which is 90, which is 115 meters. So that's how far I have traveled between the speed bump and the time I get back up to the speed of 14 meters per second. Okay, part D. Find the maximum acceleration in this period. Okay. So in that period, I'm going with this velocity. And I want to find the maximum acceleration. Well, it'd be useful to find an expression for the acceleration before I find the maximum acceleration. Okay, so it was actually useful me having written this out here. If I know my velocity in terms of t, then my acceleration will be the derivative of my velocity. Acceleration is the rate of change of your velocity with respect to time. It is dv by dt. So all I need to do is differentiate velocity with respect to time, and I've got acceleration. 15t squared over 100. The power comes in front, so 15t squared over 100 becomes 15t to the power of 1 over 100 multiplied by 2, so 30t over 100. Minus t cubed over 100 becomes minus t squared over 100 multiplied by 3, so minus 3t squared over 100. And 9 differentiates to nothing. So that's my expression for my acceleration. 30t over 100 minus 3t squared over 100. I want to find the maximum acceleration. If you want to find the maximum value of anything, you can use differentiation to do that. If you want to find the maximum value of y in an expression, when dy by dx equals 0, that is you'll find a maximum value. So here, if I want to find the maximum acceleration, I want to know what dA by dt is, and I want to know when that is equal to 0. So I need to differentiate again. 32 over 100 differentiates to just 30 over 100, or 0.3, or 3/10. Minus 3t squared over 100 becomes minus 6t over 100. And I want to know when that is equal to 0. So 30/100ths minus 6t over 100 equals 0. And that, if I solve that correctly, t is equal to 5. So the maximum acceleration will be when t is 5. Okay, and when t is 5, does it want me to find the maximum acceleration? Yes, it does. Find the maximum acceleration. So when t is 5, I need to find the value of the acceleration. So I substitute into this, which is my expression for the acceleration, and I get 0.75. So the greatest acceleration I have during that period of 10 seconds is 3/4 of a meter per second per second. Okay, part E, the last part of the paper. If all drivers decelerate and accelerate in the same way as Paul, sensible Paul. Suggest a maximum distance between bumps to ensure that drivers do not exceed a speed of 14 meters per second when driving down the road. Okay, so here's a bump. Here's the road. Here's another bump. Here's my terrible car. Classic American car, it looks like. So when you leave this bump and you're traveling this way, you are at 9 meters per second. You travel up to 14 meters per second, but then you need to reduce your speed back to 9 meters per second. We know that it took us 50 meters to go from 14 meters per second to 9 meters per second. And we knew that it took us 115 meters to get up to 14 meters per second. So therefore, this question is simply, if everyone does what Paul does, what's the maximum distance, okay, between bumps? Well, 115 plus 50, 165 meters. Okay, because if it was more than that, then Paul would have gotten to above 14 meters per second, and he would have needed more than 50 meters to slow back down to 9 meters per second. Okay, so 165 meters is the maximum distance. And there is the paper. Okay, here's the mark scheme for that question. Quite involved, lots of lovely, beautiful calculus and algebra, SUVAT. You could have done calculus in the first part. I chose to do SUVAT. And lots of lovely calculus, integration and differentiation for parts C and D. And then just common sense for part E. If you need more practice on this, okay, lesson 45 in my channel is on SUVAT. Lesson 47 is on integration problems, so that's like part C. And then lesson 46 is on differentiation problems, that's like part D. Okay, so if you want me to do any other papers, please comment. If you think these lessons are useful, please tell your friends who are doing this course. I hope it has been useful. I certainly enjoy doing them. Okay, so good luck with exams, and yeah, all the best with your maths.